Welcome to the deep dive. Today, we're strapping in and really blasting off tackling humanity's future out there in space.
Yeah, we've been digging into a ton of sources covering, well, everything from past disasters, unfortunately, to some really wild blueprints for futuristic tech.
Propulsion systems, moon bases, Mars colonies, the works.
Exactly. And our mission in this deep dive is basically to pull out the key insights from all this material.
Understand where we are now with space travel, what the big hurdles still are.
And the ambitious, sometimes pretty surprising ways people are planning to get past them. Scientists, engineers, private companies, everyone's involved.
Think of this as your shortcut to getting properly informed about the risks and the rewards of, well, leaving Earth behind.
What drives us? What holds us back?
And what the path forward might actually look like based on, what these sources are telling us.
It's a story that mixes history, bleeding-edge tech, economics.
And even some deep dives into human behavior, which is fascinating. Okay, let's unpack this then. And I think we have to start by facing a pretty hard truth. Space travel, as inspiring as it has a history marked by real tragedy.
Yeah, absolutely. The materials, they certainly remind us of those painful moments. Apollo 1, Soyuz 1, Columbia.
But the Challenger disaster back in '86, that seems to come up a lot when people study why things go wrong in complex systems, especially with people involved.
Right, because Challenger, which, unfolded live on TV for so many,
hmm
it wasn't just about those faulty O-rings on the rocket boosters, was it?
No, and the sources we looked at, they really hammer home this concept called normalized deviance.
Ah, yes. This is where it gets genuinely interesting, because it moves beyond just the hardware failure.
Explain that a bit. Normalized deviance.
Well, as it's laid out here, it's this sort of gradual process. People inside an organization, over time, they become desensitized, maybe, to risky behavior.
So it's not like one bad decision.
No,
Yeah.
not usually. It's more like years of seemingly small compromises piling up, warnings get ignored, maybe boundaries get pushed, and eventually, that risky way of doing things starts to feel, well, normal, even if, objectively, it's still really dangerous.
So like with Challenger, engineers might have flagged concerns about the O-rings and the cold temperatures.
Exactly. But maybe managers, feeling pressure perhaps, schedule pressure, budgets, they make an exception.
And if nothing goes wrong that time,
Then doing the slightly risky thing feels a little less wrong the next time. It's that slow creep. It becomes normalized.
and the sources make the point, this isn't just like ancient history from the '80s.
Not at all. This idea, this normalized deviance, it's something organizations have to actively watch out for today.
Because the pressures are still there. Economic, social.
Oh, absolutely. Economic targets, team dynamics, maybe just, wanting to keep the project moving.
Yeah.
These things can still push people towards accepting risks they probably shouldn't.
And why should you, listening, care about this?
Well, because as we plan these incredibly complex human missions, like going back to the moon for longer stays or aiming for Mars,
Mm.
understanding how past disasters like Challenger happened, not just the technical bit, but the human and organizational stuff that allowed it. That's absolutely fundamental to preventing the next one.
It's a core lesson, really, for any high-stakes venture.
It really is. It makes you think about how we build not just reliable machines, but resilient teams and decision-making processes,
Yeah.
especially when you're operating millions of miles away.
Okay, so moving on from those important but difficult lessons, let's shift to the current landscape.
Well-
Who's actually going to space now? And what are the immediate sort of practical hurdles?
Well, today is, it's undeniably exciting. The rise of private companies has just fundamentally changed the whole game.
You mean like SpaceX?
SpaceX is the prime example, yeah. They didn't just talk about reusable rockets. They actually, made them work routinely.
And that alone is huge for costs.
Huge. It's dramatically cutting the cost and changing the basic economics of just getting stuff into orbit.
And it's not just about launching satellites or cargo anymore. Space tourism is actually happening.
It is. We've had wealthy individuals paying, millions for trips to the ISS since the early 2000s.
Right.
But now you've got companies like Virgin Galactic selling these suborbital flights for hundreds of thousands of dollars.
Quick, hop up and back down.
Exactly. And others, like Jeff Bezos' Blue Origin, they're developing their own vehicles too, like the New Shepard for those short vertical trips.
Still very expensive, obviously, but
But it's opening up access in ways that just didn't exist before, driven by private investment.
And how's NASA fitting into this new picture based on what we read?
Well, NASA's adapting. They're partnering up with these private companies, sharing expertise, buying rides,
But they're also working to keep their own core skills, right? Not just outsource everything.
Yeah, that seems to be the balance they're aiming for.
Mm.
Be a key partner, a customer, but also maintain that internal expertise. It's a shift from being the only player to being maybe the anchor tenant.
And maybe that partnership model adds some extra checks and balances too.
Possibly.
Mhm.
Having multiple groups involved, sometimes with different priorities, it can lead to more, rigorous discussion around decisions. Maybe less chance for that normalized deviance we talked about.
Okay, but even with all this progress, the sources are pretty clear. We're still a long way from space travel being, common or accessible for most people.
Oh, definitely. They really boil it down to three main roadblocks:
Richer.
safety, convenience, and cost.
Yeah.
Those are the big three.
And safety. It's not just about the launch itself, is it? Being in space is dangerous.
Very. And one surprising hazard mentioned is space junk, orbital debris.
Right. Stuff left over from decades of launches.
Exactly. Dead satellites, bits of rockets, tiny fragments from collisions.
Hmm.
It's a growing cloud of debris up there.
And even small bits can be a problem.
A huge problem. When you're traveling at orbital speeds, thousands of miles per hour, even a tiny fleck of paint can hit with incredible force.
Wow.
The sources pointed out how often space shuttle windows or radiators got hit. Sometimes they needed replacing back on Earth because of tiny impacts.
So it really is like flying through an invisible minefield.
In a way, yeah. They actively track debris bigger than about 10 centimeters, 4 inches or so,
Huh?
and spacecraft like the ISS and the shuttles before it have had to perform evasive maneuvers quite regularly to avoid potential collisions.
Is anything being done to clean it up or stop making more?
There are international efforts, yeah. Guidelines to prevent creating new debris, like deorbiting satellites at the end of their life. Cleanup is much harder technologically.
Okay, so debris is one hazard. What about just staying alive up there? The basics.
Well, that's the other massive challenge.
Mhm.
You have to bring literally everything with you.
Food.
Food, yes. A round trip to Mars for a crew. The estimates are thousands of kilograms of food alone.
Thousands. Just for food.
Yep. And water's even more critical. It's incredibly heavy to launch, so it has to be strictly conserved and recycled. Astronauts on the ISS use just a tiny fraction of what we'd use down here.
And air, obviously.
Air, yeah. Maintaining the right mix of oxygen and nitrogen, constantly scrubbing out the CO2 the crew breathes out. It's a complex life support system.
You need protection from space itself.
Absolutely. Shelter is vital. Protection from the vacuum, the extreme temperatures boiling hot in sunlight, freezing cold in shadow, plus radiation. And those micrometeoroids we mentioned.
Even a tiny hole could be fatal.
Devastatingly so. The Soyuz 11 tragedy was due to a small pressure leak. So integrity is everything.
And the spacesuits we see, the ones for spacewalks?
They're amazing pieces of engineering, basically personal spacecraft. But the traditional soft suits, the ones that look kind of bulky,
Yeah.
they're quite restrictive. When they're pressurized to protect the astronaut, they become stiff and hard to move in. It takes a lot of effort.
So are there ideas for better suits?
Oh yeah, newer designs are being worked on. And some concepts mentioned involve things like powered exoskeletons integrated into the suit.
Like Iron Man suits for space.
Sort of. The idea is they could provide better protection, maybe allow for higher pressure, but also assist with movement, making spacewalks less physically demanding.
Which could make space work more accessible, maybe, for people who aren't, peak astronauts.
Potentially, yeah. It's all about enhancing human capability safely and conveniently in that environment.
Okay, convenience.
Hmm.
That brings us to the elephant in the room, cost.
Ah, yes. Big one.
Space travel has always been, well, astronomically expensive.
Completely. The Apollo program, just to put it in perspective, cost billions back then. Adjusted for inflation, it's somewhere near $300 billion in today's money.
Wow. And the space shuttle.
Each launch was estimated around, what, $500 to $700 million? Something in that ballpark.
And that standard measure, the cost to get 1 kilogram, like a bag of sugar, into low Earth orbit.
Historically, yeah, that's been hovering around $10,000 per kilogram, give or take.
$10,000 for a kilo. That's mind-boggling.
It is. And it explains why space tourism tickets are where they are: millions for orbital flights, hundreds of thousands for those quick suborbital hops. The price tag is just the #1 barrier for ordinary people.
But this is also where a lot of the action is right now, trying to bring that cost down.
Absolutely. Reusable rockets, like we mentioned with SpaceX, that's the single biggest factor driving costs down currently. It's already made a significant difference.
And one of the sources we looked at, featuring Dr. APJ Abdul Kalam's perspective, He really pushed this point hard, didn't he?
He did. He argued that for space to move beyond just, sending up satellites information missions, he called them,
Right.
to enabling true mass missions, things like large-scale industrial activity or settlement, the cost of access needs to drop dramatically.
How dramatic.
Not just like 10 or 20%. He was talking 2 to 3 orders of magnitude.
Orders of magnitude.
Yep.
So from $10,000 a kilo down to maybe $100 a kilo.
Yeah.
Or even less.
Exactly. Maybe $200, maybe $100 per kilogram. That's the kind of radical reduction he felt was needed to really open up space.
That's like going from buying a new car to buying a, I don't know, a fancy coffee machine for the same launch weight.
That's the scale of change needed for those mass missions to become economically viable. And achieving that, well, it requires some pretty radical thinking.
What kind of radical thinking? Are reusables enough?
Reusables are a huge step, but to get that low might require more. Concepts like fully and rapidly reusable systems, the whole rocket maybe turn around in hours or days, not weeks or months, or even more futuristic ideas like these aerobic space vehicles.
Aerobic, like they breathe.
Sort of. The idea is they could scoop up oxygen from the Earth's atmosphere during ascent to use as oxidizer instead of carrying tons of it from the ground. Less weight, potentially much cheaper. These are the kinds of breakthroughs needed.
Okay, so let's imagine we do crack those huge problems, make it safer, make it dramatically cheaper. What does the actual vision for, building and living off-world look like according to these sources?
Well, the long-term vision is definitely about a sustained human presence beyond just Earth orbit, especially focusing on Moon and Mars.
And that means building actual infrastructure out there.
Exactly. Creating off-world outposts. The sources describe this future architecture that includes stuff orbiting Earth, yes, but also infrastructure way out.
Like NASA's Gateway concept near the moon.
Precisely. Gateway, maybe commercial depots in lunar orbit, or even Mars orbit eventually. Think of them as crucial staging points, refueling stations, like highway service areas for space.
And then on the surface, on the moon or Mars.
Modular bases seem to be the plan. Using technologies like 3D printing is a big theme here.
Printing habitats using local dirt.
Potentially, yeah. Using the local soil, the regolith, as building material, and power is key, maybe solar arrays where there's sun, but also potentially small nuclear fission reactors for areas that are permanently dark, like some craters near the moon's poles.
And this ties into that critical idea of using what's already there, right? ISRU.
ISRU, in situ resource utilization. Absolutely vital, you nailed it. Using lunar regolith for construction, maybe sintering it, like baking it together, to make landing pads so dust doesn't fly everywhere.
That dust sounds nasty.
Apparently, it's very abrasive. Or piling up regolith for radiation shielding. But the real gold, potentially, is water ice.
Water ice on the moon or Mars.
Yes, confirmed in certain locations, especially shadowed craters. The idea of a water-based path is huge.
Mimi.
And harvest that local water ice, you can split it into hydrogen and oxygen for rocket propellant. You can use it for life support, drinking water, oxygen to breathe.
So you don't have to haul all that incredibly heavy water and propellant all the way from Earth.
That's the dream. Live off the land as much as possible. It changes the entire equation for sustainability.
And how would these future bases actually operate? Robots doing everything.
A mix, it seems. A lot of automation for routine tasks, definitely, but also human-in-the-loop control, often by contractors potentially managing systems from Earth or from orbit for more complex decisions or supervision. The goal is making really complex operations repeatable and reliable.
I remember seeing some details about different kinds of habitats they're considering.
Yeah, like comparing the traditional rigid metal can modules versus inflatable habitats.
Inflatable, like bouncy castles in space.
A bit more sophisticated than that. But yeah, they launch deflated, saving mass and volume, then inflate once in place. They can actually offer quite good protection, potentially better radiation shielding depending on design.
And dealing with that dust problem.
Big focus. Things like designing special airlocks to keep dust out of the main habitat, maybe separate mudrooms, and those bermed or sintered landing pads to minimize how much dust gets kicked up by rockets landing and taking off.
And the moon itself, it's seen as more than just a place to build a base, right? It's strategic.
Very much so. Its lower gravity makes launching from the moon much easier than from Earth. It's a stable environment. It could become a transportation hub, a communications relay point.
And there was that idea about electromagnetic launchers.
Mass drivers, yeah.
Yeah.
Basically using powerful magnetic fields to accelerate payloads like lunar materials, maybe processed metals or oxygen off the moon and into orbit, potentially much cheaper than using rockets.
And resources like helium-3 were mentioned too, for fusion.
Helium-3 is present in the lunar regolith, implanted by the solar wind. It's a potential fuel for future fusion reactors, though fusion power itself is still a major challenge. But it's one of the long-term resource potentials people talk about.
Okay, this all sounds incredible, but getting to the moon routinely, let alone Mars and beyond. With the chemical rockets we mostly use now, it's still really slow and needs tons of fuel.
Absolutely. That's why, to truly unlock deep space exploration, reduce those multi-year trip times and cut down the sheer mass of propellant you need to launch. We need propulsion systems that go way beyond traditional chemical
Like
rockets.
ion propulsion, I think you mentioned that's already been
It
used.
has, yeah. On missions like Deep Space One, Dawn, Hayabusa, ion engines work by ionizing a gas, like xenon, and then accelerating those ions out at very high speeds using electric fields.
So not much thrust.
Very, very gentle thrust, yes, like the pressure of a piece of paper resting on your hand. But the key is they're incredibly fuel efficient. They can run for months or years, continuously accelerating.
And they build up speed over time.
Exactly. Over long missions in deep space, they can achieve very high velocities, much higher than chemical rockets can manage for the same amount of fuel, usually powered by large solar panels.
Okay, what about plasma propulsion? That sounds even more powerful.
Plasma concepts, like one called VESIRM, aim for higher thrust and high efficiency. They typically use radio waves to heat a gas into an extremely hot plasma.
Like millions of degrees.
Potentially, yeah. And then use magnetic fields to contain and accelerate that plasma out the back. The goal is much faster transit times, maybe cutting a Mars trip down significantly, perhaps reaching speeds 100 times faster than chemical rockets for some applications. It needs a lot of power, though.
And solar sails. That sounds almost poetic, using sunlight.
It's real physics.
Mm-hmm.
Photons, particles of light, carry momentum. It's tiny, but it's there. A solar sail is a huge, thin, reflective sheet.
Like a giant mirror in space.
Pretty much. It catches the sunlight, and the pressure from those photons provides the gentle, continuous push. No propellant needed, just sunlight.
And like ion drives, that gentle push adds up over time.
Exactly. In the frictionless vacuum of space, continuous acceleration means you can potentially reach very high speeds over months or years. Future versions might even be pushed by powerful lasers beamed from Earth or orbit, or maybe magnetic beams for even greater acceleration.
Okay, now let's get into the really out there concepts from the sources. Field propulsion. What even is that?
Yeah, these are definitely more on the theoretical, speculative edge. Field propulsion is the idea of generating thrust by interacting directly with space-time itself, or maybe tapping into the energy of the quantum vacuum.
Without throwing anything out the back, no propellant.
That's the holy grail concept. Breaking Newton's third law, in a sense, or finding a loophole. It's based on some very advanced, not fully understood physics. Definitely not something we can build tomorrow.
And what was that about superconductors and quantum locking?
Ah, that was a fascinating detail. Superconductors, when cooled way down, they can exhibit this effect called quantum locking or flux pinning. They basically get stuck in a magnetic field,
Stuck how?
like levitating perfectly stable above a magnet locked in place by quantum effects. It's incredibly strong and frictionless.
So could we use Earth's magnetic field for propulsion?
Well, Earth's field is way too weak for that with current tech. But the phenomenon itself, this strong, frictionless interaction with magnetic fields, it's so weird and powerful, it makes you wonder about future possibilities. Could advanced materials or techniques somehow leverage natural magnetic fields in space? Pure speculation, but intriguing physics.
And the space elevator. Still on the table.
Still a compelling long-term vision. The idea of this massive, incredibly strong cable stretching from Earth's surface way up past geosynchronous orbit, with electric climbers just riding up and down, carrying cargo, maybe people, into space without rockets. The potential cost savings would be astronomical.
But the catch is the cable material, right?
That's the massive engineering hurdle. You need a material with unbelievable tensile strength and lightness, far beyond anything we can mass produce today. Carbon nanotubes are often mentioned as a possibility.
But we're not there yet.
Not even close on the scale needed. It's a classic example of a revolutionary concept waiting for a materials science miracle.
Okay, so while we're dreaming about space elevators and quantum locking, it's really important to remember, as the sources highlight, that space programs have already had a massive impact back here on Earth.
Oh, it's truly astounding. One source mentioned a figure: over 30,000 distinct technologies originally developed for space missions are now used in everyday life.
30,000! That's incredible. Give us some examples, maybe ones people wouldn't expect.
Okay, well, how about those tiny heart pumps? ventricular assist devices used for patients waiting for transplants.
Yeah.
The tech for those highly reliable miniature pumps came directly out of NASA's work on fuel pumps for the space shuttle's main engines.
Wow. Okay, that's not obvious at all. What else?
Memory foam. That stuff in mattresses, pillows, shoe inserts.
Developed for space?
Yep. Developed by NASA in the 60s to improve seat cushioning and crash protection for pilots and astronauts.
That's wild. Things we just take for granted.
Exactly. Or think about hospital patient monitoring systems, tracking heart rate, blood pressure, temperature remotely. A lot of that capability evolved directly from the need to monitor astronaut health from mission control.
Right. Makes sense.
Even simpler things, smoke detectors became more reliable and widespread thanks to NASA needing advanced fire detection on Skylab. Teflon coatings, barcodes, even the quartz timing mechanism in watches all have significant links back to space program R&D.
And beyond just gadgets, the research done in space, like on the International Space Station, that yields unique science, too.
Absolutely. Microgravity weightlessness is a unique laboratory environment, studying how materials behave without gravity, how fire burns differently, how the human body adapts. It gives us fundamental insights into physics, chemistry, biology, medicine.
Insights you just can't get down here.
Precisely. And sometimes it leads to completely unexpected discoveries that have applications back on Earth.
And some sources even talked about space helping tackle really big Earth problems like energy.
Yeah, that concept of space-based solar power keeps coming up. The idea is you put huge solar panel arrays in orbit where sunlight is constant and unfiltered, collect massive amounts of energy, convert it, and beam it wirelessly down to receiving stations on Earth. Clean, continuous power.
That sounds ambitious.
Very, but potentially revolutionary. And if you have abundant clean energy, you could power energy-intensive things like large-scale desalination of seawater, potentially helping with freshwater shortages too.
And of course, we rely heavily on Earth observation satellites already.
Indispensable now. Monitoring climate change, tracking deforestation, managing agriculture, predicting weather, helping with disaster response, even research into potentially forecasting earthquakes or volcanic eruptions relies on satellite data.
So ultimately, the pursuit of space itself has value.
Definitely. The very act of pushing those boundaries, tackling those immense challenges, it sparks human imagination, inspires young people into science and engineering, and drives innovation across countless fields in ways you can't always predict.
And making space more accessible, more understandable to the public. That helps too.
Yeah, some research suggests that increasing public engagement and making these future visions feel more tangible can actually boost perceived feasibility and excitement, creating this positive feedback loop that helps drive progress forward.
Okay, so wrapping this all up, what's the big picture takeaway from this deep dive?
Well, I think it shows the path to becoming a truly spacefaring civilization is complex. It's definitely not easy.
Yeah, it's paved with those hard lessons from the past, like Challenger, reminding us we constantly need to watch out for complacency, for that normalized deviance in organizations.
And it still faces these really fundamental, persistent challenges. Making space travel genuinely safe for more people, making it convenient, and crucially, making it dramatically cheaper.
That cost barrier just keeps coming up.
It does. And tackling these isn't just about slightly better engineering. It requires really new ways of thinking about systems, about economics, about risk.
At the same time, it's also a future that's clearly being actively built right now.
Absolutely. Through incredible technology, reusable rockets are just the start. Through these radical new concepts for propulsion, through innovative ideas for building bases off-world, using local resources.
And through this changing landscape of governments and private companies working together, sometimes competing, pushing things forward.
It really reminds you that this dream of space exploration, it isn't just about out there. It has real tangible benefits that flow back here to Earth, improving our lives in countless ways, often unexpectedly.
And providing that spark of inspiration for the future.
Exactly.
Okay, so with all of that swirling around, here's a final provocative thought for you, our listeners, to chew on based on everything we've explored today.
All right, let's hear it.
If we do manage to dramatically lower the cost of getting to space, truly achieve that 2 or 3 orders of magnitude drop Dr. Kalam talked about, down to maybe just a couple $100s a kilogram.
That game-changing reduction.
If that unlocks this new era of space industrialization, of these mass missions, what becomes possible then, both off-world and maybe even right here back on Earth, that today we can barely even imagine?